At the beginning of 2020, the S&P 500 volatility skyrocketed as prices plunged by almost 1,000 points in 1 month. Now, if we take a look at the VIX at the same time, the expectation of future volatility based off the traded index options also skyrocketed over that time to a max of 66%. In fact, if you look across different instruments and across different time periods, you're going to notice that during periods of market volatility, when the index goes down, the VIX is going up. Now remember that the VIX is a future estimate of volatility. So why would market makers and why would trading professionals think that because volatility has materialized that it's going to continue? So in this video, we're going to explain some of the market characteristics of volatility, and then we're going to discuss how we can actually model volatility to actually pick up on some of these market characteristics. In particular, we're going to be talking about how we can actually fit the Ornstein-Uhlenbeck formula to a specific volatility index. So we're going to characterize the model with its 3 parameters to market data by using the maximum likelihood expectation method. Then we're actually going to simulate this process in Python using our calibrated parameters. Now, when we actually go about doing this, we can either make an assumption each time step and discretize to get a path over time. Now, to actually get the true dynamics, you actually need to just simulate using the continuous time Ito process, and then you can get a representation of what your volatility will be at a specific time. So importing the dependencies, we've got time, math, numpy, pandas, datetime, scipy, matplotlib, pandas data reader, and from the stats module, we've got this plot ACF function. The data we're going to import is the S&P 500 since 2003. Now, volatility clustering in financial time series. We're going to be referring to this paper, Volatility Clustering in Financial Markets by Ramakant in 2005. Now, he did a really nice literature review where he reviewed papers that proved the statistical properties of financial time series. Now, the 3 big ones that we're talking about: excess volatility, characteristics of heavy tails, and volatility clustering. Now, volatility clustering, what is that? Well, essentially, Mandelbrot described it as large changes tend to be followed by other large changes of either sign, and small changes tend to be followed by small changes. Now, a quantitative manifestation of that fact is that while returns are uncorrelated, and we'll show that in a second, absolute returns or their squares actually display a small positive correlation. Now, this is significant and slowly decays. So let's talk about log returns. Log returns are simply just this price process x, where it's the logarithm of the price. Now, this gives us the log returns over time. Now, the time scale that we're considering is the smallest time scale available to us with Yahoo data, which is 1 day. Now, as we plot that for the S&P 500, visually you can see that the magnitude of log returns here, right, are clustered together. I can see here 2008, 2009, huge cluster. Again, 2020, as we just discussed, clustered here. So let's look at the correlation of just straight log returns from each other. So as you can see, this first one is itself with itself. So of course it's 100% correlated with itself. But then with one lagged version and then all these other lagged versions, there's almost no autocorrelation. Interesting to see here that over this specific data range, we've actually got a little bit of a negative correlation. But in general, there is no autocorrelation that's statistically significant. So now by squaring the log returns, what I care about now is the absolute magnitude and the correlation between them during periods of volatility. And what you can see here, we've got very strong correlation between even lagged days up to several weeks. And this is an interesting fact to be observed. So what this is really saying is that during periods of large volatility, it's likely to continue. And then during periods of low volatility, it's likely to continue. So autocorrelation of the absolute magnitude. So this is called volatility clustering. So now if I want to see the rolling volatility over a number of days, I have to pick a trading window to compute the standard deviation over, and then I annualize it by taking the square root of a year. So 252 trading days in the year. Now, as I can see, I've had some really huge upkicks in realized volatility. So what I want to do, I want to actually model this realized volatility process. So what is a way that I can do this? So now we're going to talk about the Ornstein-Uhlenbeck formula and how we can actually use this to model volatility. Well, essentially what we're most interested in is its version here with this extra drift term, and this is known as the Weissach model in financial mathematics. Now what we have is we've got kappa, which is really the rate of this mean reversion process. we've got the average, which is this theta, and then we have the volatility around this average price, which is called sigma. So this stochastic differential equation, what we want to do is we actually want to get values for those parameters that maximize the likelihood of being from this distribution that we're observing. So how do we do that? Well, maximum likelihood estimation, MLE, is actually a method that we can apply to realize data, random samples that we have, to a specific probability density function. So let's talk about the probability density function of a normal distribution. This will become evident soon. So here is the normal distribution function. And if we have a bunch of random samples, which is y1, well then the joint probability density function, or the likelihood function, is actually represented by this f here. So it's multiplying, so it's the product of all the individual samples given the parameters that we have here, denoted by theta. So this is called the likelihood function. So basic understanding is that the likelihood function is the density function regarded as a function of the parameters. So we have this likelihood function in terms of theta given our realizations x, and that's equal to our observed joint probability distribution function. So the maximum likelihood estimator is going to be the parameters that, with the data that we're given, actually maximize this likelihood function. So in terms of our parameters that we're going to test, what maximizes this probability density function, or the joint probability density function? What we do is we actually take the log of that function, which is equivalent to finding the same maximum. Now, the reason we do that is because we get a desired property that instead of having to deal with the products here, we get to deal with the sum of the log of the PDFs. So here, it doesn't actually matter what PDF we're actually looking at. It doesn't need to be normally distributed. We can still consider the MLE process as long as we consider the residuals to be normally distributed. So for something that's continuous and differentiable, like the normal distribution that we saw above, so if we use the process of Lagrange multipliers, which is we take the partial derivatives of this continuous differentiable function, the PDF, and make it equal to 0 for our interesting parameters, then we'll solve for the MLEs. So what I'll do is I'll take the likelihood function of our mu and sigma, and what we're going to do is just multiply the PDFs by each other for each x realization all the way to xn. If you then collate all these terms using a bit of algebra, you can get this formula on the right hand side there. Now if you take the log of these terms, then you can actually get it in this form here. And this is now easier to derive. So sometimes, as we've said, this isn't going to be differentiable, but in this case with the normal distributions, we can actually use Lagrange multiplier method to find the maximization parameters. So here, you find the partial derivative, you make it equal to 0, and then you find that the maximum likelihood functions for both the mu and the sigma, so the mean and the volatility, is actually the mean of the data that we observe. And then the volatility, the variance, is going to be the squared error. So if we actually place this into the process, we've got the MLE of the normal distribution. So we just take the mean as our MLE for the mu, and the sigma hat is our var. Now this is the biased estimator, wherein we're not accounting for the degrees of freedom. So we make sure that that runs. Now we're actually just going to test how we would estimate this process. We've got mu equals, so we've got our normal distribution process that we're going to sample. I've got a mu of 5, sigma of 2.5. I'm taking 10,000 samples. I'm seeding my NumPy randomization process with 0, so I get the same thing every time. And here I'm just getting a whole bunch of random normals. Then what we're going to do is we're going to use the maximum likelihood function to return what my expectation is. My estimates are for mu and sigma too. And what we get is in fact very close estimates of 4.95 and 2.47. So now we're going to perform it numerically. And now why would we want to do this? Well, like we said, sometimes it's not differentiable, the log likelihood function, so you actually need to find a numerical solution to this maximization problem. So the maximization problem of the log likelihood is also the minimization of the negative log likelihood. So because we only have SciPy optimize minimize function available to us, we're going to minimize the negative log likelihood. So to calculate log likelihood from our two parameters, theta, we have mu and sigma, and then we place that into the SciPy stats norm PDF, for our observed x values. Now that gives us, we're going to take the log of those values and then we're going to take the sum of those values. So we're taking the sum of all the log probabilities that the values that we observe come from the distribution where we have parameters set as mu and sigma. So the only constraint I'm going to add is that sigma needs to be positive. So the way that you actually add a constraint is you have a dictionary and the type is an inequality in this case because I want it to be greater than 0, and the actual function that I'm going to be assigning is this sigma positive, where sigma needs to be greater than 0. Now I'm actually going to define SciPy optimize minimize. I define my log likelihood function, then I just define the initial parameters. My arguments, which are passed through to the log likelihood function, is x, and then the constraints is the constraint set, just my one dictionary here. So we've just discussed how we can use the maximum likelihood estimating functions to actually estimate the parameters of a normal distribution process. But what's the distribution function of an Ornstein-Uhlenbeck process? Well, essentially we've got to use Ito calculus to find the dynamics of this xt process. So to get our expectation and variance of this Ito process. First step in actually doing that is we're going to rearrange this equation, the Versailles equation, and what we do is we just expand the brackets, move our xt to the other side. So what we recognize is that the partial differential of e to the kt, kappa t, of xt is actually equal to the terms that we have on the left-hand side multiplied by this exponential term. So what we can do is we can multiply through by the exponential term, and then we can take the integral over the time period 0 to t. So then we have the differential of these terms here is equal to the right-hand side multiplied by the exponential terms, and we have the integral from 0 to t. Now the next step is to actually take the integral over the real Riemann integrals of this equation, so not worrying about the Ito integral yet. And what we get here is we've got the exponential of kt of xt minus x0 and then e to the 0, which is just 1. Now that's equal to k0, and we have e to the kt minus e to the 0, which is 1. Now doing our final bit of arranging here, all I need to do is then take all the terms to the right hand side and divide through by the exponential term here. So now that we've actually got the Ito process in terms of these integrals here, we can actually now go ahead and find the expectation and the variance of this process. So the expectation is really simple. All we do is we drop off this dynamic diffusion term here because the expectation of the Wiener process is 0, and then what we're left with is the drift term that we had in that Ito process. Now for the variance, all we need to do is take the expectation of the square of xt minus the expectation of xt. So all you need to do is substitute in xt and ext from above, and then you're left with essentially the diffusion part, the Ito integral of the equation above. Now I know that the only terms left because of Ito's lemma in all these cross multiple terms with dwt and dt is going to be dw, which is equal to dt. And the reason that this exists is because of quadratic variation. So now the variance is then equal to this term here, where we've got our dt term left. We've taken the square down into the exponent and the square of the sigma. So here, if we take the integral, then we get t minus t, so the exponential of 0, which is 1, minus e to the negative 2 kappa t. Now, because this is an Ito process, and I've just calculated the expectation and the variance, I know that this is normally distributed because Ito processes are a martingale under the risk-neutral measure. So I've got this xt process with my mu and sigma with the expectation and the variance as described above. Now what I can do is that I can do a translation of this variable which has the same distribution as mu plus sigma zt, where zt is the normal distribution. So therefore I can get this discretized equation of the true process between time steps. This is the formula that I'm going to be using for the MLE of the Ornstein-Uhlenbeck process. So let's now consider what the actual PDF is of the Ornstein-Uhlenbeck process. So again, we've got this process here, which is normally distributed with this expectation and this variance. So if we just remember back to the PDF of the normal distribution, which looks exactly the same as this, now we're actually parameterizing the normal distribution in terms of the parameters that we want. So we need xt, which is the previous data point, we need kappa, we need theta, and we need sigma. Now, the sigma hat here is going to be the standard deviation from this variance process here that we've defined, which is just sigma square root of these terms here. And then the expectation, the u hat, is going to be equal to this process here, the expectation of the Ornstein process. So we have a normally distributed variable, but now in terms of our parameters with the different expectation and a different variance estimator. So I'm going to write this in Python. I just need to define this mu that takes in x, which is the previous data point. It takes in dt, it takes in kappa and theta. Now the standard deviation takes in dt, the time difference, kappa and sigma. And I'm just returning these two equations. Now for the log likelihood, what I need to define now is that for all my parameters, I need kappa, theta, sigma. I also need to differentiate between the next data point, which is my dt, and then, so here I can just do that by using a numpy array, starting from the time 1 slice, whereas the previous data point starts from index 0 and only goes to the second last indices slice. So that's xt. Now the time difference between all the data that we're observing here, of course, we know is 1 day, and we have 252 trading days in the year. So of the Ornstein-Uhlenbeck process, the mu and the sigma is defined using those functions that I defined above, and then we can calculate the log likelihood function of the theta parameters by actually taking the SciPy stats normal distribution PDF, but with the location as the mu that we've defined here and the sigma that we've defined here. Now we also take in the time steps that are one ahead of our delayed process that we're feeding into the calculation of the mean. So just be careful there. We're also taking the negative of that log likelihood function. We have two restrictions here. We've got kappa positive and sigma positive. So if we run these functions now, I just want to remind you that we're taking that volatility index. So the pandas data frame of volatility above, we're just turning that into an array. And then now I have those two constraint sets here, kappa pos and sigma pos, as inequalities. My initial guess for all the theta parameters is just 1. Now, same process as before, I got the log likelihood, but with our new function here, and then the constraint sets. So using the historical volatility, we actually get these calibrated parameters for our process. And what that is kappa is 0.5, which is that, every half a year we have this mean reversion. And then the mean reverting process has a mean of 0.16, and it has a standard deviation of 0.107. Now, finally, we're going to talk about how to actually simulate this process in Python. Now, if you want to do a perfect simulation where you're getting the correct distribution of the Ornstein-Uhlenbeck process, it's very important that you actually do the continuous time stochastic process. Now, what I mean by that, you can't discretize this process because you're having to make a Euler time step adjustment approximation. To actually get the true process, you need to just take from time 0 where you are and use the continuous time stochastic process to go forward in time to time t. Now, if we just want to go ahead by 0.2 years, we have 1,000 variables. We're going to model that using the random normal distribution, assign that to the z value for m variables. Then we've got our two functions, mu and standard deviation here, which is just part of our Ornstein-Uhlenbeck process. So we've got kappa, theta, time, our x variable, our lagged x variable that you're requiring, kappa and sigma. So as we assign the drift and the diffusion terms to those two functions, we can then calculate the volatility as just the drift plus the diffusion term multiplied by that standard error. So by plotting a histogram, we can see that the volatility has a distribution like this for the Ornstein-Uhlenbeck process that we've actually tuned to our market volatility. So there are actually two ways that we can implement this discretize STE. So the only difference between what we're doing above and here is that we want to see the paths in Python. Now there's two ways to do it. Essentially here we just add in an extra dimensionality, which is the n, the number of time steps that we want. Now because it's recursive, we've either got to use a recursive function like I've done here, and this can be very efficient and it's obviously very clean in terms of a code perspective. So what we have is we've got time, we've got the volatility that we're passing, and then we're using the recursive function to actually increase the time and then repeat the process until we hit our end time step. So at each time what we're doing is we're updating our parameters, our drift and diffusion, and taking our stochastic process, our stochastic time step. So for those interested who want to compare the recursive function to the Python loop, which is just running through the time steps for each of these different simulations, feel free to compare. So here we've looked at how we can actually model volatility and get our optimized parameters using MLE for the Ornstein-Uhlenbeck process. Now, this has been really important because we can have applications in many different areas of financial mathematics. And next week, we're going to be talking about how we can actually do option valuations using this model in something called the Hurston model. So until next time, YouTube, see you later.